In this video we're going to have a look at the different number systems that we use. The first one we're going to look at is the decimal ordinary system, which is sometimes called base 10. And this is the one you'll be most familiar with. First of all, we need to think of the values of the different units. So across the top we're going to start off with units. So we'll have it as ones. Then tens is the next unit it represents. Then increases by 10 as well, which is why it's called base 10. It goes from 1 to 10 to hundreds, to thousands, to 10,000s, and so on. So if I want to represent the number 67,000, I would have a 6 in this, representing 60,000, and a 7 in here, representing the 7,000, and 0, 0 in here, representing 0 hundred, 0 tens, and 0 ones. And obviously if I wanted to change that to 60,001, I would scrub out the 0 in here and put a 1 in there. So that's called base 10. That's the decimal ordinary system. This is the most popular numbering system used. And the key thing to get is it's increasing by 10 each time. So 1 goes to 10, increasing by the power of 10, base 10. Then it becomes 100, 1,000, 10,000. That is decimal ordinary. The decimal ordinary system. The next number system we're going to look at is called binary, which is also known as base 2. In the previous example of base 10 increased by 10 each time. So again, we're going to start in the right hand column with a 1, and we're going to increase that to the power of 2, which is going to give us 2. And the next one we're going to increase 2 by the power of 2, which is going to give us 4. So it's just doubling each time by the power of 2, 8, 16, 32, 64, 128. And again, this will continue to go on and on if we needed it to. So that's the values of the different digits. So in terms of computers, we like things which can be turned on or off. So we like saying either this value is on or this value is off. To say that a value is off, we simply use 0. So this would be the binary representation for 0, as every one of these values is turned off. Now if I wanted to change that and have a value of 32, I would rub that one out and I would turn it on. So it's now worth 32. If I wanted the value of 36, I would have to rub out the 4 and turn that on. And again, if I wanted to add up the value of 37, we're going to need to include the 1, so we're going to switch that from off to on. So that's kind of what the 1s and 0 within binary represent. And again, we've got 128 over this side. That's the highest value in this particular one. So we add up the different ones that we want to actually get the number that we need. Fairly straightforward. Sounds complicated, but it's not. 0 indicates it's not important, it's not included in the value. 1 means include this part, this number. So 1 will be 32, means 32 will be included. 128 won't be, 64 won't be, 16 won't be, 8 won't be, 4 will be, 2 won't be, and 1 will be, which will obviously give us a number of 32 plus 4 plus 1, which will give us 37. So that's binary or base 2. Remember, doubling up each time. 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32, 32 to 64, and so on. The next number system that we're going to look at is called octal, and that is known as base 8. Now we've looked at base 10, which is increasing by 10 each time. Base 2 is increasing by the power of, not increased by 10, sorry, increased by the power of 10 each time. Base 2 increases by the power of 2 each time. Base 8 similarly will increase by the power of 8 each time. So again, we're going to start with a 1 in the right hand column. We are then going to have an 8. Let me just move that, sorry. Erase that, move it up a bit. So in the right hand column we're going to have 1. The next column we're going to have 8. 8 to the power of 8 is 64, so that's the next column. And the next value is going to be 64 to the power of 8, which is 512. And again, this would continue on. And how does this work? Similar fashion to binary, and a little bit like denary as well. Actually, the main difference between this and binary is we can have more than one. There's more than just ones or zeros. We can include everything up to the value 7. So just to illustrate that, if I click on the eraser, if I want the value 3, for instance, I am going to have it like this. I'm not going to need 512, 64, 8, but I am going to need 3 number 1s. If I want the number 7, I am obviously going to need 7 1s. If I want the number 8, I'm going to not need any 1s. I'm going to knock the 1s off. I'm going to put that to 0, and I'm going to put 1 8. And again, if I want 63, I'm going to need 7 8s. It's going to be 8, 16, 24, 32, 48, 56, 56. So I'm going to need 7 in here, and I'm going to need 7 1s as well on top of that to get up to 63. So that is octal or base 8. Similar idea, it increases by the power of 8 each time, and we can go up as far as 7 in each one of the digits, the values for each digit. The next number system we're going to look at is known as the hexadecimal system, which is base 16. So in the same fashion, we're going to start off with 1 in the right hand column. To the power of 16 is going to give us 16, and 16 to the power of 16 is going to give us 256. And again, that will continue up. And let me just draw my squares. Now this is where it gets slightly different approach. If you think about it, we can only contain one digit in here, which is going to be somewhere from the value of 1, and in this current one at the minute, the highest value we could have in is 9, which means we will not be able to get a lot of numbers, because obviously we're going to need 10 16s for 160, 11 for 176, etc. So there's going to be a lot of numbers missing. To combat that, in hexadecimal we also use letters. So we use the characters, the numbers 1 to 9, to represent, as they usually do, the values 1 to 9. The next thing that we do then is we use the letters A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, F is equal to 15. So we use the letters A to F as well. But these actually represent the numbers 10. So it sounds a little bit complicated, but it's not. It comes down to the idea that we can only have one character in each of these, one bit, one digit. So how's that going to work in terms, if we want the number 10, for instance, obviously 1 to 9 is going to be the exact same. We're going to have 0, 0, we can have 1, or alternatively we can have 9 in here. If we need the value 10, obviously 9 is not going to be enough, and we can't do any other way of getting it apart from use the letter A. So that would be the value 10. If we wanted 10 plus, let's say we wanted 26, so we're going to erase, we're going to turn that off, and we're going to put on a 1 for that. So these can go up from 1 to 9, as shown over here, and then A equals 10, B 11, C 12, D equals 13, E equals 14, F equals 15. And then obviously we would just switch over to the next column. So 15 would be the highest value we'd ever need in 1 would be F is equal to 15. If we needed 16, we would put 1 in here and turn this one off to 0. So again, sounds a little complicated, awkward mixture of numbers and letters, but a fairly straightforward idea and concept. The next number system that we have to be aware of is known as the binary coded decimal. In this one, we can represent the numbers of 0 to 100, and it works slightly different than standard binary. It breaks the digit into two different values to to represent the first and second digit of the number. So to explain, we've got 1, 2, 4 and 8. So this is all we need to get up to the value 9, 8 and 1. That will represent the second digit, and in the same way the first digit will be represented in this block of 1, 2, 4 and 8. So if I wanted the number 20, I don't know why I've done that. If I wanted the number 26, I'm going to get a 2 in this one, which is going to be 0 1s, 1 2, 0 4, 0 8s, and I want a 6 in this one, which is going to be 0 8s, 1 4, 1 2 and 0 1s. So this binary code represents that value, the second number of the decimal number, of the actual number between 1 and 100, and this one represents the first number. So again, sounds a little bit complicated, but it's just breaking it down into 2 4-digit bits and using that to represent the first and second digit of the number. That's called binary coded decimal. We're now going to look at two different methods of representing negative numbers. The two we need to be aware of are the sign magnitude method and the 2's complement method. First of all, we're going to look at sign magnitude, and this works pretty similar to binary. It's increasing by the power of 2. So it's 1, 2, 4, 8, 16, 32, 64. The key difference is it uses the first bit to represent either a positive or negative value. So there is no 128. It's positive slash negative. So we just draw that out and see what that's going to look like. So obviously if we want the positive value 35, we're going to turn on 32, plus 2 gives us 34, and we're going to turn on 1, which gives us 35, and we're going to have zeros for the rest. So that's going to give us a positive value of 35. Now this bit is extremely important because it will determine whether the number is a positive or value. If we want it to be positive, we set it as 0, so that would be positive 35. If we want it as negative 35, we turn on this digit. Yeah? So again, sounds complicated, but it's fairly straightforward. Works up the exact same way as binary does. The only difference is the first bit, the first digit, represents either positive or negative. 0 for positive, 1 for negative. The key limitation of this method is we can't, as we don't have the value 128 that we would have in binary, we obviously can't count up the same value of numbers. So that's called sign magnitude. Another way we can represent negative numbers is called 2's complement, and there are two main steps in doing a 2's complement. The first one is we get the value. So in this one I'm going to use the numbers, I'm just going to use 3-bit numbers. So the value 1 is going to be 0, 0, 1. The value 2 is going to be 0, 1, 0. The value 3 is going to be 0, 1, 1. Just for the example, that will do for now. So 2's complement, the first thing is we get the positive value. So if we want 2, we will get 1, there are 0, 1, 1. 0, 1, 0 is going to be the value 2. Obviously we've got a 1 here, 2 there and 4 up there if we want to draw it out that way. And then what the first step we do now is we flip the bits, which basically means if it's a 1 we change it to a 0, if it's a 0 we change it to a 1. So we're flipping this round, so 0, 1, 0 is going to become 1, 0, 1. And then we are simply, so you can see what's happening there, we flipped the 0 to a 1, we flipped the 1 to a 0, and we flipped the 0 to the 1. And the next step we have to do is to add on the value 1. So if I just quickly draw that down here as a binary representative of the value 1. We now add these together. It's important we remember how we actually add numbers in binary. So if we've got two zeros, it becomes 0. It stays 0. 1 plus 0 equals 1. 0 plus 1 equals 1. And if it's 1 plus 1, then we get, for instance, in this part here, we're going to make this one equal to 0, and we're going to add a 1 in here. So this value is then going to become 1 plus 1 is going to be 0, and it's going to carry 1 over here. 1 plus 0 is going to be 1. So originally that would have been 0, 0, but because we've got to carry 1, that's 1 and 0, and then this one is going to be the same. So that is 2's complement.